And we will go from current slide. All right. I guess a projector will come on. I was making fun of it earlier, but I was just kidding. Okay. Guess you know about the good news, bad news situation coming up next week, right? All right. The good news is that the 4th of July is next week, and we have the day off. The bad news is it's on a Wednesday, and that means we missed class. So sorry about that, but get over it. Okay. Now, yes, we got a projector now. Can't think of anything else that we might need to know about now, but let's pick up if there's no questions about what we've done so far. But let me say this while I'm thinking about it. This my second largest class, I believe it is. Awfully close to it anyway. And we're basically, I think, past midterm now. And I've only received one research paper in. One, okay? And that means that you have only the month of July left, basically, to get your paper in. So please get it in sooner rather than later, okay? That's the first thing. Second thing, the first test. Maybe over half of you, more than half of you have turned that in, and I've already given you the second test. Now, is anyone here that didn't get the second test? Okay, let me make sure. That was the one thing I said you could take extra time if you need it on the first test, but please try to get it in before we finish the second chapter and get going on that. So let me get these returned to you. Okay. Anyone else? Anyone else? Okay. So need those first tests in, folks, because guess what? If you missed some concept and botched it up on the first test, now you're working on your second test, you don't know you missed the concept, I can't return those until I get them all in. Okay? So please get your papers in. You may be hurting a fellow student rather than yourself, but don't do that either. All right, any questions before we get going? All right. We were talking about relative extrema and critical numbers. Now we get to the definition, even though we've talked about it. As long as this function f is defined at c, okay, has some definition there, and if that f prime of c is 0, the first derivative is 0, what does that mean to you? First derivative is 0. What's first derivative represent? Slope of the tangent line. And if it's 0, what does that mean?
It's undefined.
No, it's not undefined. That's next. Huh?
That's what tangent line. That's 0.
Okay, the slope is 0. And what does that mean?
Opposite.
Horizontal tangent line. Horizontal tangent line. So if the f prime of c is 0, meaning a horizontal tangent line at 0, or if f is not differentiable at c, okay? Another way of saying that, not defined at c, then c is a critical number of f. Now remember, f is defined at c, so it can't be not differentiable because it's not defined. It must be defined there, but being defined there doesn't mean it will also be differentiable there. Then c is called the critical number of f. Notice that the definition above, the critical number c has to be in the domain of f, but c does not have to be in the domain of f prime, meaning it's there, but not necessarily there. Now let's see. I think I've seen him before. Yeah, here he is. Okay. All right, let's see. Good deal. All right. Here's theorem 3.2. Relative extrema occur only at critical numbers. Now that doesn't say absolute extrema, the relative extrema. Okay, remember what those were? Those are the places that are relative minimum or maximum, not the endpoint values, but somewhere in between. The relative extrema occur only at critical numbers. if F has a relative minimum or a relative maximum, x equals c, that means it's an extremum, then c is also a critical number of F. Now, important thing here, don't read too much into this. Just because c is a critical number, by this definition, doesn't mean it's necessarily a relative extremum. Okay? So don't go too far with it. But if it is a relative extremum, it is a critical number. Okay? But not all critical numbers will produce relative extremum. All right, we'll see that in a minute. Now, this is on the top of, by the way, there's a little blurb on the side of the page, Pierre de Fermat. Okay? Trained as a lawyer, but he had a hobby of mathematics. Okay, that's a rather strange way to look at things. But he loved mathematics, but he played around with it, okay? And in playing around, and he had some really good friends who were very good mathematicians, and they fed off each other. And he contributed to analytic geometry, number theory, calculus, probability, and generally did it in letters to friends, okay? He wrote many of the fundamental ideas of calculus long before Newton or Leibniz, okay? And this theorem we just did is often, the one I just went past, often attributed to Fermat, okay? So, there is a little proof in the book on that last theorem, well worth taking a look, and I think you'll see it pretty much makes sense, but let's move on. How do we find these extrema on a closed interval? Okay? Hopefully you've already gotten a clue or two. Now, theorem 3.2 states that the relative extrema of a function can occur only at the critical numbers of the function. Knowing this, you can use the following guidelines to find those extrema on the closed interval. Closed interval. Okay, to find the extrema of a continuous function f on a closed interval a to b, here are the steps. Find the critical numbers of f in the open interval a to b. How do we find those? How do you find your critical numbers? What's the good answer in this class? Take a derivative, okay? And what two cases do you look for in the derivative? Say again? What two cases do you look for?
If it's zero.
If it's zero or
Not
the
good.
derivative not defined. The function must be defined, but if the derivative is not defined, then those are the two things. So there's your first step. Find the critical numbers. That's how you find them. Okay? Now, evaluate f at each critical number. Okay? Once you find the critical number, go back and plug in what x is and find, now it's c, and find out what the value for x is, the y value. Evaluate f at each endpoint. Okay? Remember, we're on a closed interval, and we're looking for an extrema there. Your critical points will be the things on the inside. Your endpoints will be possibilities. Not definites, but possibilities. Now, the least of these variables, now we're talking about absolute extrema here, the least of these values for f at each of the critical numbers and at each of the endpoints. The least of those numbers is your minimum, and the greatest of those is the maximum. So it's pretty straightforward. Okay? Let's try it. Find the extrema of f of x is equal to 3x to the fourth minus 4x cubed on the interval -1 to 2. Where would you begin? Any ideas? I can't get my pen. There we go. Nothing. This thing is so stinking slow today. Okay. There we go. I don't think it's quite in sync. It's jumping around like crazy. What's the first thing we do? Take a derivative. Excellent answer. L prime of x. Okay, and what is that? 12x cubed minus squared. Very good. All right. Now, what do we do with that derivative once we found it? Say again? I can't hear. Okay, you certainly can factor it. But what's the ultimate goal? What are we going to do to that? Two things we look for in the derivative. Oh boy, it's been at least 3 minutes. A long time ago. Two things we look for in the derivative. Read the top line. Where the derivative equals 0 or where it doesn't exist. Okay? Those are the two things we look for. Okay? And that's the reason we're going to factor it. You set it equal to 0. Now factor it. And what do you get? Factor that. Factor it. Use your idea. 12x squared. And what do you have left? A little louder? X minus 1. Very good. And is that equal to 0? And Daniel's here. Okay. There's that. All right, pretty good attendance today. Way to go, folks. Okay. Now what do we do with it? Second. Yeah, find the x values that make that 0. What are they? Second. X equal 1 is certainly 1. No others? Anybody? Help them. What other x would make that equal 0? Okay. Your rule for is called the zero product principle. You have two factors here. Say again? I can't hear you. Okay, and what's the other one? Okay. You set 12x squared equal to 0. And then I heard you say divide by 12. That's okay to do too. Okay, 12s go out, and 0 divided by 12 is 0. Okay, so now we got x squared equals 0. Any ideas what value x might be to make x squared equal 0? 0! X equals 0 is the other one. Okay, so I'll just lose the square there. Actually, it's a double root, by the way. Okay, so now we found your two values of x's for which it's 0. Those are critical values, right? Those are two of your c's. Now, are there any places, what was the second condition about that first derivative? Either where it's equal to 0 or, what was the other one? Where it, say again? Where it's not defined. This is a polynomial function. This derivative is a polynomial function. Polynomial functions are defined everywhere, all real numbers. So there's no problem there with not being defined. So we got our two critical numbers. They're both where the slope is 0, or the first derivative is 0. Okay? What other two x values do we include in our investigation? Second, -1 and 2, your endpoints. So those are the other two we're going to investigate. And by the way, these two values here, your critical values, have to be in that interval. They are, so that's fine. We'll also look at x equal -1 and x equal 2. Okay? We evaluate our function, the original function at each of those. Let's start with -1. F of -1 is equal to what? All right. Better, right? All right, good deal. What is f of -1? 7 is what I heard. That was 3 minus a minus 4 is indeed 7. Very good. Okay, what's the next one you want to investigate? One of my favorites. Alpha of 0. What is this value? 0. Hey, quick, okay. And then another one. Alpha of 1. And what is that value? Negative 1. And finally, alpha of, only one we have evaluated. 2 that I hear. Okay. Now, that's the hard one. Okay, because it's bigger numbers. Okay, what's 2 to the 4th power? 16, is that what I heard? Okay, 16 times 3. 48 minus 2 cubed is 8.
16.
Huh?
Your answer is 16.
The answer is 16. Okay. 48 minus 32, 16. Great. All right. Now what we're looking for are your extrema. That means the extreme values for F. What's the minimum in all those values? Negative 1. So your extrema is at the first, at one critical point, x equal negative 1, and that's your relative minimum, absolute minimum in this case, in this interval, and the other. What's the other extreme? Say again?
16.
That's 16, and that's where x is equal to 2. So they are a relative extrema. The absolute minimum at 1, absolute maximum at 16. At 2. Okay, sorry. It is 16. Now, yeah. It is 16, but it's located at x equal 2. All right. Let's see how they did it. Any questions before I erase it? What's that? No. The question, find the extrema. These are these two are critical numbers. Those are the endpoints. We evaluate the function of each of those to find the absolute minimum and the absolute maximum. So these are your actions. Absolute minimum at x equal 1, absolute maximum at x equal 2. And the values are negative 1 and 16. So let's see how they did it. Okay. All right. Begin by differentiating the function. But they wrote it first, okay? Write the original function. That's really good. Okay, then differentiate it, and they got the same thing you did. Excellent. Then they did what to it? Set it equal to 0. To find the critical numbers of F on any interval, you must find the x values for which the first derivative is 0 and all the x values for which it doesn't exist. So we'll start with setting it equal to 0, and that will be at 12x squared. They factored just like you said, and then they set them equal to 0 and found x equals 0, x equals 1. Yes, those are the two critical numbers. I like to call them values, but they call them numbers. Okay? Now, because f prime is defined everywhere, it's a polynomial function. Defined everywhere, those are the only critical numbers. If there's any place that first derivative was not defined, that would be a critical number. But it's defined everywhere. Okay? So, then they picked the endpoints, x, negative 1, and positive 2, and they did the same thing we did. Alpha of negative 1 is 7, alpha of 0 is 0, alpha of 1 is negative 1, and alpha of 2 is 16. Okay? Which of those is extreme? Extreme minimum is negative 1, extreme maximum is 16. So the values at which those occur are at 1 and 2. So let's see. Oh, and then they draw the graph. Interesting little graph here. Here's your interval from -1 to 2. Here's your two critical values, x equals 0 and x equals -1. X equals 1. Yeah, x equals 1. Okay, it's valued at -1 there. Now, something to note about this one. That's neither a relative maximum. It looks like it's going to be a minimum, but then it looks like it was a maximum. It's neither. But it is a critical number. But remember, Fermat's theorem, or whoever's that was, said that all your relative maximum and minimum will come at critical values, but they didn't say that all the critical values will produce a relative minimum and maximum. This one does not. But if you're looking for your absolute minimum and maximum, you must then also include the endpoints. At -1, you're up here at 7. 2, you're way up there at 16. So therefore, here's your minimum, there's your maximum. Those are your extreme values. And really the best way to say it, 1, -1 is the minimum, and 2, 16 is the maximum. That way you get both the x value and the y value. Okay? Make sense? Yay or nay? Okay. Here's example 2. In figure 3.5, which we just did, note that the critical number x equals 0 does not yield a relative minimum or a relative maximum. So just because it's a critical number doesn't make it a relative minimum or max, but all your relative minimum or maximum will occur at critical numbers. So it goes one way but not the other. This tells you that the converse of theorem 3.2 is not true. You can't guarantee just because it's a critical number that you're going to have a relative minimum or maximum. But if you have a critical number, let me say that the right way. All the relative minimum or maximum will occur at critical numbers. Just because you have one doesn't guarantee it's there. In other words, critical numbers of a function need not produce relative extrema. I think we've said it about 15 different ways now. And that's the last slide. They skipped example 3 and 4. So let's go back and do example 3. I think we can't go any further here. Okay? Example 3. Find the extrema of f of x is equal to, see they showed on the slide set the easy one, the ones that are a little more complicated they left off. 2x minus 3x to the 2/3 power. Okay? And we're doing this on the interval -1 to 3. What's your approach? We're looking for the extrema, meaning the absolute minimum, absolute maximum on that interval. What's our first step? Take a derivative. Sounds like a winner to me. Okay? F prime of x is equal to 2. Help me. Say again? A little louder.
I think it's 2.
I can't hear you.
I think it's 2.
Yeah, minus 2 x to the minus 1/3. Perfect. Okay? And what do we do? You found the derivative. What do we do with it? Second? I don't believe it'll factor, but we, second? Set it equal to 0. That's what we're looking for. Places where the derivative either is 0 or does not exist. Okay, let's deal with the 0 first. How would you solve that? Okay, yeah, factor out of 2. So your factoring is a good idea here. 2 times what? 1 minus x to the minus 1/3, okay, is equal to 0. Now, Okay, two factors here. First we'll deal. Can 2 ever be 0? Not in this universe. So that's not a possibility. Here's the one that is. And what I was just about to ask is, do you think in terms of negative exponents, or do you think more in terms of radicals? Especially when you're trying to solve something. You tell me.
So if you're trying to solve something?
Second?
Like if you're just trying to...
Yeah, we're going to try to find values of x that makes that true. Do you want to leave it in radical notation, in exponential notation, or you want to go back to radical? Second?
Exponential.
You do, okay. We'll do it. All right. So your other factor is 1 minus x to the minus 1/3 is equal to 0. How do you solve that? Second, okay. That's one thing you can do. X minus 1 over x to the 1/3 is equal to 0. Is that what you meant? Is that what you meant? Oh, you said move the 1 over. I'm sorry. I'm sorry. I thought you said put 1 over. Sorry about that. Okay. My hearing is bad. Sorry. Okay.
You just move the negative x across the equal sign.
Okay, let's add x to the minus 1/3 to both sides. And that will give us x to the minus 1/3 is equal to 1. Okay. Now what? Okay. He's going back to radical, it sounds like. Let's do that. What does this mean? 1 over, what did you say? The cube root of x. Isn't that x to the 1/3? Negative 1/3, right? Is equal to 1. Okay. Now what? Now what? Multiply both sides by the cube root of x. Okay, and what does that give us? I'm going to switch sides again. The cube root of x is equal to 1. Right? Now what? Cube both sides, right? Undo the cube root. Okay, and when you cube the cube root of x, you get? Nope. X. And when you cube 1, you get 1. There we have it. All right. X equal 1 does solve this thing, and 1 is in the domain between negative 1 and 3. So we found our one and only one critical, no. We found our one and only one place where the first derivative is 0 in this problem. Or is that your only critical value? What was the other case for your taking your first derivatives? Where the first derivative was 0 or
Undefined.
where it's undefined, exactly. So let's go back to our first derivative. Okay, we set it equals 0 here. This time, let's check and see where it's defined. F prime of x is equal to 2 minus 2, and this time I'm going to put it over the cube root of x, right? Now, you tell me, is there any value where that is undefined? At 0, definitely at 0. I've got a problem, Houston. It's also undefined at any negative pattern, right? Yeah, so we got a whole bunch of them, but certainly at 0, okay? Not at all defined for any negative value. The function's defined at 0, and the function's defined at, oh, wait. You let me do that. That's a cube root, not a square root. It's cube root, okay? Okay? Like that, that's a cube root. Cube roots are defined at negative values, but still denominator can't be 0. So the one and only problem here is x equals 0. So that's the one place where this is not defined. So there's another critical value. This produced x equal 1. This one produced x equal 0. 1 is where you have a horizontal tangent, slope of 0. The 0 is where your derivative is undefined. The function is defined there, but the derivative is not. Okay, so we got two candidates. Any others? Say again?
How you get x equals 0?
Okay. How did I get this? Is the critical value here? Okay. Because the first derivative here, we got where it's equal to 0, that produces x equal 1. Right? Okay. The other condition is where this first derivative is undefined. So I wrote the first derivative in this form, 2 minus 2 over the cube root of x. Okay, cube root of x. The minus sends it downstairs, and the 3 is your index. Now, where is this undefined? You can never, ever, ever divide by 0. So when x equals 0, that's undefined. See? But cube roots can be positive or negative. There's no problem there. Or the rack of what's inside can be positive or negative. It's only even roots can't be negative. Okay. So the only place this is not defined is x equals 0. So we have two candidates for our relative extremum, maximum or minimum. Are there any others? The what? -1 and 3, your endpoint. Remember? Those are also candidates. So we'll also investigate x equal -1 and x equal 3. Okay, which one you want to start with? -1. So what is, you go back and plug them in, f of, I have to write x, no, it's f of -1. I erased too much. Is what? This is the original function f. This one. Plug in -1. What do you get?
1.
Okay. That starts with a -2, right? Minus 3 times the cube root of -1 is, okay, I'll write it in. And again, I like to evaluate. I don't like radicals, but to me they're easier to evaluate. This is the cube root of x squared. Right? That's what x to the 2/3 is. Right up here is the cube root of x squared. Or the cube root of x squared. You can do the square either on the outside or inside. I find it usually a little easier, but it depends. Sometimes it's easier to do it on the outside. Since it's a -1, it's not too bad anyway. So the first part was I've mixed my metaphors here. This is the -1. I didn't put that in. So let's go and put in the other. What happens? This will be a -2 minus 3 times the cube root of a -1 squared. What's that? -2 minus 3 times, what's the cube root of 1? 1. So this comes up being -5. Whew. All right, took us a while, but we got there. Which one would want to do next? Second? You want to do 3 next, okay, jumping way up to 3. So f of 3. What's that going to be equal to? It's 2 times 3 minus 3 times, now this, yuck. This is, yeah. It's the cube root of 9. 3 squared is 9. And that's just not a very handy number. I don't know what it is. Okay? Pull out your calculator, see what it is. 6 minus the cube root of 9. Someone with a calculator, give me the answer. 6 minus 3 times the cube root of 9. Say again? Anyone got it? No one with a calculator. Okay. Oh, one person with a calculator in a math class. Oh, 2 people with calculators. Someone give me an answer. Okay, now write it from the book. What you get? Yeah, it will. I don't think you have that cheap a calculator, but we'll see. In the book, they got negative 0.24. Okay? In other words, the 3 times the cube root of 9 is a little bit greater than 6. Not much, but a little bit. What's the next one you want to do? You've done the 2 endpoints. What other point might you choose? Say again? 0? Is that what you said? I'm sorry?
I said 2.
2. Was 2 one of our critical, or?
It's on the interval.
We had x equal negative 1, we've done. X equal 3, we've done. X equal 1, we haven't done. And x equals 0. Okay. Say again? Which one you want?
We haven't did 1 yet.
No. Haven't done 1, we haven't done 0. Okay, do 1. Alpha of 1. Oh, that one's pretty easy. What is that? Say again?
-1.
-1. Perfect. Because 1 to the 2/3 power is 1. X is 1. Okay. 2 minus 3 is -1. And the last one is alpha of 0. And what's that?
0.
Oh boy, y'all put off the hardest till the end, didn't you? Okay, that's 0. Now, the question is, of these 4, which is the absolute maximum? 0. Okay, what's the absolute minimum? -5. So those are the 2 first points of interest. At -1, -5 is one extremum, that's the absolute minimum, and at 0, 0, that's your absolute maximum. This is a pretty negative function in that range, okay? Because you're, yeah, it just is. Let's see what they got in the book. Yep. You conclude the minimum is alpha of -1 equal 5, and maximum alpha 0 is 0. Good for them. Okay? Let's do example 4. You need this up any longer? Anybody? Okay. Example 4. And this one, by the way, is located at larsoncalculus.com for an interactive version of this type of example. Maybe not the same one, but this type. Find the extrema, that means absolute maximum, absolute minimum, of this function, alpha of x is equal to 2 sine x minus cosine 2x on the interval 0 to 2 pi. Now, let me remind you, if it's a closed interval, we do investigate at those endpoints. If that was an open interval, we only look at the interior points, which would be your critical values. You don't consider the endpoints. Okay? So let's go from there. Well, I may want to take that back. You still look at them, but they can't be the relative extremum. I shouldn't have said that in first. What do we do first? Take a derivative. Alpha prime of x is equal to what? 2 cosine x is a good start. I can't write. Okay? Plus, say again. I know there's a sine 2x in there. Anything else? Say again. Y'all don't like chain rule, do you? Is the chain rule part of it? This is a function of a function. Cosine is the outer function. What's the inner function? 2x. You need to do the derivative of 2x. What's that? Second? 2. Exactly. So you also have a 2. So I left room for it. Okay? Okay. Good question. Yeah. Let's review the chain rule quickly. If you're taking derivative d by dx of f of g of x, okay? Well, I wrote it, but it didn't show up. What that gives you is f prime at g of x times g prime of x. Okay. Outside. Okay? So, your outer function here, that's the f, is the cosine function. Derivative of that is minus sine of the same thing, of g of x, that doesn't change. And then you do times the g prime. Now, g prime is 2. If you put the times 2 out there, that gets really difficult to figure out what you're talking about. So move the 2 over here so it's clear 2 times that. Because this is, in this case, 2. 2 times this other thing. Here's the other thing, 2 times it. Does that answer what you're saying? Yeah. The 2x stays in here because it's the outer function is taken of that. Then the derivative of the inner function. You could write it over here, but it's clearer if you put it in here. Okay? Now, what do we do with that? We found the derivative. Yay! But what do we do with it? Set it equal to 0. That's one thing we want to do with it. Set it equal to 0. Then what would we do? Factor it. Okay? Well, is it okay just say, well, I see a common factor of 2. So let's just get rid of the 2. Divide them out, divide by 0, and it's still 2. I mean, still 0. Okay? You did it. Factored them and divided them. They're gone. Okay? What's wrong with this picture, though? Cosine x plus sine 2x is equal to 0. I want to do some more factoring, but I don't see any common factors at all. Do you? What's a problem with this? What's a little messy about it? Your cosine function has this argument. Your sine function has a different argument. Sort of be nice if they were all the same argument, right? Do you remember anything about a double angle formula? No. Huh? That's it exactly. It's 2 times the sine x cosine x. So this is cosine x plus 2 times the sine x cosine x. And set that equals 0. Now I like it better because now we've got the same functions. And now what can we do? Factor out a what? A cosine x. And what does that leave us with? 1 plus 2 sine x. Don't forget your 1. That's equal to 0. Now what do we do? You factored them. You wanted to factor them. We factored them. What do you do with it? Set each of them equal to 0. The only way a product of two things can be 0 is if one or the other is 0. So either cosine x is equal to 0 or 1 plus 2 sine x is equal to 0. Okay? Now, here's where we go back to our interval. Where in that interval is cosine x equal to 0? Where is cosine equal to 0 on the interval 0 to 2 pi?
Pi over 2.
Pi over 2 is 1.
2 pi over 3.
Second?
2 pi over 3.
2 pi over 6, is that what I heard?
3.
3 pi over 2. Okay, yeah. 3 has pi. Okay? Your cosine starts at 1, it's 0 at pi over 2, then it goes down to -1 at pi, and then back to 0 at 3 has pi. By the time it gets back to 0, you're outside the interval. So this has two values, x equal pi halves, or 3 has pi, in that interval. Okay? Now, what do we do with the second equation there? What do we do with the second equation there? Help me, help me. Say again? I still can't hear. -1. Subtract 1 from both sides. Okay, good deal. And what does that leave you with? These go away. 2 sine x is equal to -1. And now what do we do? Second, divide both sides by 2. Okay, that's nice. That gives me sine x is equal to -1/2. Where in the world on that interval from 0 to 2 pi is the sine -1/2? Okay, I thought. Okay. All right. Let's picture what the graph of sine looks like. It starts and goes up. There, it's never negative in that first pi. Never negative. It's only negative in the second two quadrants, quadrant 3 and 4, right? And it's -1/2 somewhere here, somewhere there, just before it gets to 2 pi. What are those somewheres? Okay. What did you say? 7. One more time. 7 pi over 6 is definitely one of them. Okay, x equal 7/6 pi. That's the first one you get to, and the next one is at 11/6 pi. Wait, 11 pi over 6. I can't write. Okay. Perfect. Okay. All right. Someone was paying attention in trig class. Okay. Now, we have 4 candidates for where your derivative is equal to 0. Okay? What other condition do we consider? Where it's undefined. Okay? Now, is there any place where this derivative is undefined? With sines and cosines, find everywhere. If you had a tangent in there, whoop, secant, whoops, cosecant, whoops, cotangent. Those have undefined values. Sines and cosines, you find everywhere. So no, we don't have to worry about that for these. So we have 4 candidates here. Any other candidates for our extreme values? 0 and 2 pi. So we have this, x equals 0 or 2 pi. All right, where do we want to start? 0. So let's do f of 0. Now, I'm running out of room, so I'm going to get rid of my chain rule review. Is that okay? Okay. I think I'll move this up some. Okay, since I got rid of that. Let's do f of 0. All right. Here's your f function. Plug in a 0 here. What's sine 0? Sine of 0. 0 with great confidence, okay? What's sine of cosine of 0? 1, but you have a minus, so that'll be a -1. Okay, everybody agree? -1. Okay, which one you want to look at next? 5 more to choose from. You pick one. Help me, help me. Say again? I couldn't hear. You want to do 2 pi next? Okay, we'll do 2 pi of 2 pi. I hope I can just write down what the answer is, but let's plug it in and see. What is sine of 2 pi? 0. And what's the cosine of 2 times 2 pi would be 4 pi. Okay. But the minus makes it 2, it's minus 1, 2. Guess what? These are sine and cosine functions, the period of 2 pi, and this one's actually 4 pi, so yeah, it's going to be fine. It's got to be the same value. So that's also a negative 1. Okay? So we've got both of those being negative 1. What you want to look at next, you're putting off the ones you have to struggle with, right? And it's not big a struggle, by the way. What you want to consider next? Pi over 2, okay? F of pi halves. And what will that be? What is sine of pi halves? 1. 2 times 1 is 2. What is cosine of, is pi halves, but double it, and you got pi. What's cosine of pi? Negative 1. But you got a minus there, so that would make it a positive 1. So you got 2 plus 1 is 3. Okay? So alpha pi halves is 3. Looks like we may have a candidate for a maximum, but let's see what you want to consider next. You want to jump to 11 pi 6? Fine, I'm all in favor. Alpha of 11 pi 6, or 11 6 pi, however you want to say that. All right, this will probably take some thinking now, okay? What is the sine of 11 6 pi? Negative 1/2. Remember, that's how we got it, all right? 2 times that would be negative 1. So hang on to that. What is, okay, first, what is 2 times 11 6 pi? Two times 11 6 pi. Oh, fractions are fun, aren't they? Is what? 2 times 11 6 pi. That's the one you wanted me to do. That'd be 11 thirds pi, wouldn't it? The 2 cancel into 6 3 times. 11 thirds pi. Now there, I'm going to have to do some thinking. Okay? All right. And I think the best thing to do here is go to the unit circle. You okay with the unit circle? We love the unit circle, don't we? Okay? Now, we're talking about 11 thirds pi. A third of a pi is approximately there. I mean, I probably did it too much. 2 thirds pi would be there. 3 thirds pi here. 4 thirds, 5 thirds, 6 thirds. 7 thirds, 8 thirds, 9 thirds, 10 thirds, 11 thirds pi. Okay? And what's the cosine of that value down there? I'll give you a hint. It's negative, right? So it's going to be a minus. Now, here's what I fall back on. Say that again. That's it. Negative 3, square root of 3 over 2. Okay? Okay. So, where was I? Oh yeah, cosine of that, negative square root of 3 over 2. That's, okay, that, okay. And we have a minus already, so that makes a plus square root of 3 over 2. And I've almost forgotten what the first one was. What was that? Had we done it? That was a negative 1/2 times 2. That's a negative 1 minus that. No, plus that. Yeah, plus that. So it's root 3 over 2 minus 1. Okay? Is that right? It was, but you see we have the minus sign in front of it. Yeah? Right? Okay. Everybody in agreement now? Okay? We've done 4 of the 6. Okay? This could take a while. Which one you want to do next? Doesn't matter to me too much. No, it doesn't matter at all. Pick one. There's two left. Pick one of them. 3 pi over 2. Got it. Okay, so f of 3 pi over 2. All right. Go back up here. And what is sine of 3/2 pi? Negative 1. Is that right? Did we do? Oh no, yeah, sine. Okay, I'm sorry. Okay, sine of 3 pi over 2 is negative 1 times 2 is negative 2. So that part's negative 2. Now 2 times 3 pi over 2 is 3 pi. And what's cosine of 3 pi? Negative 1. Okay? And minus that would be a plus 1. So this was a negative 2 plus 1 is negative 1. Okay. So here we have another negative 1. That seems to be a very popular answer here. And the last one, I'll pick this one. That's going to be 7/6 pi. 7 pi over 6. All right. All right. And let's plug that in here. What is sine of 7/6 pi? Negative 1/2. That's how we got it. Times 2 is negative 1. So we got our negative 1 there. And what's 2 times 7/6 pi? 7/3 pi. Okay? Let's go back up here. 1, 2, 3, 4, 5, 6, 7. We're up there. First quadrant. Okay? What's the value there? Cosine of 7/3 pi? Or that actually the same as 1/3 pi is what? Square root of 3 over 2. Positive, but we got a minus sign in front of it. So we have a, what was this, a minus 1, was it? Minus square root of 3 over 2. So this gives us minus 1 minus the square root of 3 over 2. Okay. Now, I was going to say I might need some help, but I think I can pick out the maximum. Can anyone? Yeah, that's that. So here's our maximum. Now, the minimum might take a little more effort. I think we can rule out this one. Because the square root of 3 over 2, square root of 3 is 1.7 or something like that. Over 2 is a little bit less than 1. Subtract 1 from it, you have a small decimal number. That's not, it's going to be less than negative, greater than negative 1. So, but it's pretty obvious to me this has to be your minimum, right? Yeah, all these are negative, and that was negative 2, so you're absolutely right. That's going to be your max. So here, min. This is the max, and this is the min. Okay? All right, let's see how the book did. The maximum was at pi halves at 3. Good for them. Ooh. Yeah, okay. I'm sorry, you're right. My picture was bad. This was my bad all the way around. My pictures stink, okay? It was not root 3 over 3, root 3 over 2, but 1 over 2, right? I was thinking sines. We were doing cosines. This is, so go back here. You led me astray, but this is, yuck. These are 1/2, not root 3 over 2. And I think we might have messed something else up here. Let's go back to 11/6 pi. Sine of that was negative 1/2. I'm sorry, yeah, negative 1/2 times 2 is a negative 1. Okay, we got that part. And the cosine of that was 11/3 pi Oh, and we were down here. Okay. 11/3 pi is down here. Remember, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Down here. Cosine down there is positive 1/2, but you got a minus sign in front of it, so this was a minus 1/2 too. So both of these are minus 3/2, and both of those are your relative minimum. Okay, sorry about that. You have two relative minimum. These are both negative 3/2. Sorry about that. Now, if you look in your book, they show you the picture of it, and by far, pi halves is the big winner as far as relative is absolute maximum on this interval, and your 7/6 pi and 11/6 pi are tied as relative minimum at negative 3/2. Sorry about that. Okay, so if you're using calculators, you probably would have avoided that error. Okay, but my pictures were pretty ugly. Okay, now that finishes 3.1. Any questions on it? Homework exercises here. Any of the odds, 7 through 11, they're all at Calc Chat. 7's at Calc View. Either 13 or 15, they're both at Calc Chat. Any of the odds 17 to 21, they're all at Calc Chat. 17's at Calc View. Any of the odds 23 to 39, they're all at Calc Chat. 25's at Calc View. Either 41 or 43, they're both at Calc Chat. 41's at Calc View. Either 45 or 47, they're both at Calc Chat. Neither are at Calc View. Do 49, it's at Calc Chat also, but not at Calc View. Do 51, it's at Calc Chat, but not at Calc View. Do 53, it's at Calc Chat, but not at Calc View. And then you can look at 55 and think through it if you want to. I wouldn't probably spend a lot of time on that. And then exploring concepts, if you want to think through those, you can. I don't know how much of Calc Chat of them are there. You might find something that would be helpful or interesting, but I'll let you decide that. Look at 59, though. I do think that's an interesting question. Okay? I'm going to clear this and consider the function alpha of x is equal to, goodness, this is it Caleb? No. Huh? You did say Caleb, right? Huh? Caleb. Yeah, okay, that's what I had said. I had you, now I've lost you. There you are. All right. Good deal, folks. We're only missing Taylor, is that right?
That's Taylor right there.
Oh, you're Taylor. Okay, I'm sorry. I can't hear, and it seems like I always miss, so we're only missing Caleb. Okay. Unless she comes in the next few minutes. Wow, great attendance today, folks. Okay. Now, what I was going to look at is number 59 on page 172. Page 172, this is 3.1 exercise, I think is what they call these, don't they? Yeah, exercises. And this is number 59. Consider this function, f of x is equal to x minus 4 over x plus 2. Okay? And it said, if that was your problem and said find the critical numbers, what would you do?
Usually we try to take the derivative.
Okay, you definitely would take a derivative. And what kind of rule do you think you're going to need to take that derivative? Quotient rule, probably. I knew no one would want to do quotient rule, okay? So yeah, so let's do quotient rule. How does that go? How does it go? Huh?
It's going to be x minus 4.
Derivative of x minus 4, is that what you said? Or you said x minus 4?
Let's do x minus 4.
Okay, do x minus 4
Times.
times.
That's just going to be 1. Actually, the other way.
Okay, it's going to be 1.
And then minus.
Okay.
That's going to be x plus 2 parentheses.
X plus 2. Is that what you're saying? I can't hear well.
Over x plus 2 squared.
Okay. He likes the quotient rule, and I don't blame him. It's a great rule, except you get it backwards. It's low D high. You start with this and derivative of that. This should be the plus. That should be the minus. Minus high D low. High D low. Okay. That's the only way that little thing, I find it sort of silly, but it helps me from making a mistake. So this is the plus, that's the minus. Okay. Now, the only question they ask here, if I look at this derivative, I can look at this and so I know this derivative is not defined at x equal negative 2, right? So therefore, is that a critical number? Huh?
No,
That's what?
Yeah.
Why not?
Isn't minus 0?
Yeah, but that's where you're looking. The critical numbers where it's equal to 0 or not defined. I know it's not defined at x equal negative 2. So is that a critical number? Why not?
It's not going to be defined at 8.
It's not defined up here either. That's the key. That's the answer. X equal negative 2 is not defined for your function, so don't even consider that as a critical number. Okay? That's the only reason we did that. In fact, as soon as you write this down, whether the book writes it or not, you should say x cannot equal negative 2, because you know it can't. So don't proceed with your derivative, even if you do it wrong or whatever, and come up and say, oh, but there, here the derivative is not defined there. So what? The function's not defined there. The function must be defined. So that was the point of that one. Just because the derivative is not defined at x equal negative 2, the function wasn't, so that doesn't make it a critical value. It makes it not even considered a value. Sorry, I shouldn't have gotten off into that. But anyway, from there, I think you can do number 61, 63, and 65 and 67 are true false. I would think through those. 69 is sort of a thinking type problem, and then there's the Putnam challenge only if you want to look at it. That's it for 3.1. Any questions? All right. Let's go on to, boy, this is taking forever today, 3.2. Okay. I was going to try to go a little faster, and I think I've bogged down pretty badly. Okay. This is the kind of section I like to move through a little bit faster. If it'll ever open. My word, things are taking forever today.
It's going to take a while.
What's that?
I said it seems like it's going to take a while. You want to take a break or?
Okay, yeah. This would be a good break time if someone wants to take a break. So I'm all in favor. So while that's trying to open itself, all right. All right, chapter 3 is applications of differentiation. The first was finding your maximum and minimum, extreme values. 3.2 is now going to talk about two other features. One is called Rolle's theorem, the other the mean value theorem. These are other examples where we use the first derivatives, differentiation. Okay? So our two objectives are first to understand and use Rolle's theorem and to understand and use the mean value theorem. Well, what in the world is Rolle's theorem? And by the way, who in the world was Rolle's? I don't have a picture of him. French mathematician Michel Rolle first published his theorem that bears his name in 1691. Before this time, however, Rolle was one of the most vocal critics of calculus, stating it gave erroneous results, was based on unsound reasoning. Later in life, Rolle came to see the usefulness of calculus. So he was a doubter, but then he came around. Okay? So, this, besides being called Rolle's theorem, is called the extreme value theorem. It states that a continuous function on a closed interval a to b, okay, count the endpoints, must have both a minimum and a maximum value on that interval. Hey, we've been saying that all along. Both of these values, however, can occur at the endpoints of that closed thing. If there's an open interval, they may not have a maximum and minimum, okay? Because it could have been at those endpoints, but it's not included, okay? So Rolle's theorem, named after him, gives the conditions that guarantee the existence of extreme values in the interior of a closed interval, not at the endpoints. So here's what Rolle's theorem says. If f is continuous function on this closed interval a to b, differentiable on the open interval a to b, so it's differentiable everywhere. So now what we rule out, derivatives can't not exist here, okay? Derivatives have to exist. So if f of a, the endpoint, and f of b are the same, then there's at least one number c in a to b, the open interval a to b, such that f prime of c is equal to 0. Okay? That's Rolle's theorem. And you might say, so? Well, what this tells you is the first root has got to be 0 at least one place there. The reasons, it's a continuous function, that's one. Can't have any breaks in it, okay? Differentiable on the whole interval a to b, so if it's continuous and differentiable there, and f of a is the same as f of b. Okay, you got two possibilities. The simplest thing would be that's a straight line there between a and b. And they're the same value. First root is 0 everywhere. Okay? Everywhere. The function is constant, so the first root is 0. So that would be an extreme case. But any other case, whatever the function is doing, remember it has to be continuous and differentiable. So that means smooth and continuous. If it's going down here, it's going to have a 0. If it's going up here, it's going to have a place where the derivative is 0. If it's doing all sorts of wiggly things, it's going to have a lot of places where the first derivative is 0. Because they have to be, f of a has to equal f of b. That was in his theorem. Okay? From Rolle's theorem, you can see that a function f is continuous if it's continuous on a, b, and differentiable on the open interval a to b, and if f of a is equal to f of b, that's the key here, there must be at least one x value between a and b in which the graph has a horizontal tangent line. And we just, sort of arm-waved our way through that. But the key here is f of a and f of b have to be the same value. And if the function is continuous and differentiable, that means smooth and continuous, either it's going to be a straight line where every point the derivative is 0, or it's going to do any number of other things, but it must be smooth and continuous to have a derivative everywhere. So there's going to be several, at least one place where it has a horizontal tangent. It could be a relative maximum, relative minimum, and it could be any kind of in between. But remember, there is no place where the first derivative doesn't exist because it said it's differentiable on a to b. Okay? Now, when the differentiability requirement is dropped from Rolle's theorem, you still have a critical number here, but you see Rolle's theorem says it must be differentiable. Okay? But it may not have a horizontal tangent. This is a relative maximum. In fact, it's an absolute maximum. Okay? But the first derivative doesn't exist. So you can't say f prime of 0 is going to be 0, because it's not anywhere on that. Okay? So that doesn't fit Rolle's theorem. Why in the world did they put it in here? Okay? I guess showing you why they put the differentiability in there. Okay, here's example 1. Find two intercepts of f of x is equal to x squared minus 3x plus 2. Find the two x-intercepts of that function. Frankly, I don't see any calculus in that part. Do you? How do you find the x-intercepts? What are x-intercepts? This is an algebra problem. What are the x-intercepts? Where? What's true about an x-intercept? Any kind of an answer will do. Okay? Say something. Say again? Okay, where your y is equal to 0. F of x equals 0. Set it equal to 0. It's exactly it. Because the x-intercepts are where the function crosses the x-axis, right? That's what it means. It intercepts the x-axis. So anywhere on the x-axis, y is equal to 0. And what is your y? Tell my pre-calculus algebra, this is the main thing you have to remember in the whole course. Y is equal to f of x. Set that equal to 0, you're absolutely right. Okay? So let's do that. Whoa, let me get my pen back. Okay? So set this equal to 0, and what does that give? What will you do next? Say again?
Move the 2.
I can't hear. Sorry.
Move the 2 or factor.
Oh, you're factoring it, okay. X times x, and it's a minus and a minus. And did I hear a 1 and a 2? Was that right? Is that right? Okay. So the two x-intercepts would be x equal 1, x equal 2. Two x-intercepts. Did that? Did. Okay. Now I'll show that f prime of x is equal to 0 at some point between those two intercepts. Well, guess what? If they're x-intercepts, they have the same value. Y is equal to 0. Okay? So they have the same y value, 0. By Rolle's theorem, it's a continuous function. It's a polynomial. They're always continuous. It's differentiable. Polynomials are always differentiable. Okay? You have 2 points with the same y value, so in between there's got to be at least one value where the first derivative is 0. And really, that's all you have to do. You've met the requirements. X equal 1, x equal 2, the y value is the same, it's 0, and it's a continuous function, it's a differentiable function in that interval, and so therefore it has to have at least one value. Anyone want to hazard a guess where that would be? Just knowing what kind of function that is? What kind of function is that? Maximum exponent of 2. Second? What was it?
I said binomial.
Okay. Those two are binomial functions. This is a trinomial. But it's a quadratic function. What does a quadratic function always graph as? A parabola. And parabolas are always have a line of symmetry. Right? The line of symmetry is going to be between two. So guess where that's going to have its max or min at x equals 1.5. Got to. Because it has equal values there, it's going to have its either peak or its valley in between the two. Which will it be? A peak or a valley?
Valley.
A valley. Why do you say valley? Yes, because the A is positive, opening upward. You're absolutely right. Okay. That's all review. Okay. So let's see what they say. Note that f is differentiable on the entire real line for They're all real numbers. Setting f equal to 0 produces x minus 1 times x minus 2, x equal 1 or x equal 2, x equal 1, x equal f of 1 and f of 2 are equal to each other and both equal to 0. That's why we picked them out. From Rolle's theorem, you know there exists at least one c on the interval such that f prime of c is 0. Find that value, okay? Now I did it the easy way, okay? But they want you to find it now, and they didn't say to do this, but let's go back and do it. Okay? How do you find that? Where f prime is 0. How do you find where f prime is 0? What's your good answer? And that way f prime is. F prime of x is equal to?
0.
Second?
0.
Okay, but do it. What is f prime of x?
2x minus
2x minus 3. Set that equal to 0. So you're right to do it, but get the derivative first. Solve for x. And what would you do? Okay, add 3 to both sides, and that gives you 2x is equal to 3. What's x equal to?
x equal to
3 divided by 2, 3 halves, which is 1.5, which is exactly what we said before, just by reasoning, knowing it's a parabola, okay, equal to 3 halves. Okay, now how do you determine if that's a max or a min? Plug it in, plug it in. So f of 3 halves, f now, is 3 halves squared minus 3 times 3 halves plus 2, which is what's 3 halves squared? Help me, help me. 3 halves squared. 9/4 minus what's 3 times 3 halves? A little louder. 9 halves plus, I'm going to write that as 8/4. Is that okay? That's 2, isn't it? Right? Now we got 4s everywhere but there. This will make this 18/4. Is that right? Okay. Now, add these two together and you get
9 plus
add 9 plus 8, yes. 17/4 minus 18/4, that's going to be minus 1/4. So that's the maximum, the minimum value. Okay? Because it was 0 at x equal 1, x equal 2, negative 1/4 down here, so it's the minimum value. Right? Yay or nay? Okay. Good deal. So let's see what else they did. Okay. To find the value c, take the derivative and set it equal to 0. You set x equal 3 halves, and x equal 3 halves, your value is negative 1/4. So sure enough, that is a minimum value. But we knew that already because your coefficient a here was positive, meaning it's opening upward. That has to be a relative minimum. Okay? In this case, an absolute minimum, no doubt. Okay. Any questions? That's one fairly simple example of Rolle's theorem. Okay. Before we go to the mean value theorem, let's do example 2. Not on the slide set, so let's do it here. Let f of x equal to x to the 4th minus 2x squared. Find all values of c in the interval minus 2 to 2 such that f prime of c is equal to 0. Okay? Find the value C's on that interval where f prime for C is equal to 0. Okay. Where would you begin on something like that? Anybody? Take a derivative is always a good answer, isn't it? F prime of x is equal to
4x3 minus 4x.
Okay, and then what do you want to do with that derivative?
Take out 4x.
Second? Okay.
Take out 4x.
Okay, let's first set it equal to 0 so that factoring makes sense. Okay, you can factor anything, expression, but why you're factoring it is because set it equal to 0 so you can find the zeros of it. Okay, so like you said, factor out of 4x, and what are you left with?
X.
X what?
Oh, x squared.
Squared minus 1. Okay, are you through factoring? Why not? That'll be what?
On the x intercepts.
Okay, and what would they be? Can you factor that any further?
Yeah.
What?
You get x plus 1, x minus 1.
Okay, and that's equals 0. Okay, now what are the values that make that first root of 0 then?
Say it one more time.
What are the values of x that make that 0?
1 and negative 1.
Second?
1 and negative 1.
Okay, certainly x equal 1 and x equal negative 1 certainly will make that 0.
X equals 0.
And x equals 0 makes it 0. Okay, we found 3 values, and guess what? They're all in that interval from negative 2 to 2 for which the first derivative is 0. You know, that's what the problem asked for. Did we ever call on Rolle's theorem to do that? No, we didn't need to do this, what it said. Find the value C on that interval, negative 2 to 2, for which the first derivative is equal to 0. Just take the first derivative, set it equal to 0, see what values make that 0, and throw your calculators around, okay? And it's a pretty easy thing to do, right? So, why was Rolle's theorem needed in this case? It really wasn't. Note that it satisfies conditions of Rolle's theorem. Fine, but who cares? What difference does it make? That is, f is continuous. Certainly it's a polynomial function on that interval and everywhere. Differentiable on that interval and everywhere. Moreover, because f of minus 2 equal f of 2, both equal to 8, you can conclude there exists at least one C in that interval, okay? But they didn't ask any of that. They just said find the values. So you didn't have to do anything else except take a derivative, set it equal to 0, and find the values, okay? Yeah, all the rest of what they said was true, but it's fine. Now, they show you a technology pitfall here. Graphing utility can be used to indicate whether the points on a graph in these two examples are relative minimum or maximum, okay? But it said, however, should keep in mind it can give misleading pictures of graphs. For instance, this weird one they give here, it's really weird. With most viewing windows, it appears it has a maximum of 1, okay? But it really doesn't, okay? So you can read through that if you got a graphing calculator, and that's what you're depending on. Beware of that. It's a strange function, and that's what makes you miss it. Okay, that's it for Rolle's theorem. So let's move on to the mean value theorem. You have a lot of mean values out there. You have to watch out for them. No, I'm just kidding. What this means is average. Not that it has any negative connotations to it. The average value or mean value theorem. Rolle's theorem can be used to prove another theorem, the mean value theorem. And here's what it says. Starts out very similar. F has to be continuous on some closed interval a to b. It has to be differentiable on the open interval a to b. Same start that Rolle's theorem has. Exactly the same. What it doesn't have is the f of a equal f of b. That was required in Rolle's theorem. It's not here. So what are we going to get at? Then there has to exist a number C somewhere in that open interval a to b such that f prime of c is not 0. The f prime of c is the same slope as between a and b. In other words, y2 minus y1 over x2 minus x1. F of b minus f of a over b minus a. Okay? So if you have a function, and you know it starts here and ends there, okay? Well, the slope of that is that slope right there. F of b, that's a negative slope. F of b minus f of a, that's a negative number. B minus a, yeah, it's a negative slope. Well, this function, whatever it's doing in there, has at least one place where the first derivative is also that same negative slope. Why? It's continuous. Can't have any gaps in there. Differentiable. Okay? It's going to have at least one place where it has the same slope as that. All right? So here's example 3. And by the way, they have a little blurb here. I keep mentioning these little blurbs. You can find potential paper topics here. Joseph Louis Lagrange. Okay? Has a pretty prominent nose, doesn't he? Okay. The mean value theorem was first proved by Lagrange, born in Italy. Lagrange, which sounds like a French name, but that's a very Italian nose, isn't it? Held a position in the court of Frederick the Great in Berlin for 20 years. He was one of the Holy Roman Emperors. I can remember my English teacher in high school said, yeah, they called it the Holy Roman Empire, but it was not holy, it was not Roman, and it wasn't an empire. So, but that's what they called it back then. But that's who Frederick the Great was. So he was a sort of court mathematician. Okay. And they do a little proof here, and I'll let you read through it and see what it is. Let's move on to example 3, which is on page 177. By the way, this example is also our clarsoncalculus.com for an interactive version of this type of an example. Okay. So here's what we got for f of x is equal to 5 minus 4 over x. Okay. Find all values of c in the open interval 1 to 4 such that this is true. Now, this again is an example that as soon as I see that function, it's a good practice to get into, folks. Look at that function, and what's the first thing that should come to mind when you see this function? X cannot equal what? 0, because you can't divide 4 by 0. Okay? So when I see a function like this, just like that other one I showed you earlier, x couldn't equal -2. This one, x can't equal 0. Write that down so you don't get pulled into something that's going to be a bad place to be. And then as soon as I read the next part on the open interval 1 to 4, whew, good deal, folks. If that had been the open interval -1 to 4, hang it up, Jack, okay? Because that concludes the 0. You can't do that, okay? This 1 to 4 excludes 0, so whatever they're going to do here is going to be okay. All right? It says find all the values of C on the open interval such that f prime of C is the slope of your secant line between those 2 points. F of 1, F of 1, and 4, F of 4. Okay, first thing we better do then is find out what, okay? Let's find out what F of 1 is. What is it? Help me. 1, okay? What's your F of 4? A little louder. Second? 4. Perfect. Okay? So what's your slope between those 2 points? That's what this thing is here. Alpha 4 is 4. Alpha 1 is 1. And 4 minus 1, this would be 1. Okay? So it says find all the values C on the open interval 1 to 4 such that f prime of C. So the next thing we got to do is find out what f prime is. Okay, what is f prime? First, I'm going to rewrite f. Okay, I do not like variables in the denominator. So how might I rewrite this to make it easier to differentiate? 5 minus 4, rather than putting it over x, how could I write that x? Okay. For differentiation purposes, I don't like that expression. I want to rewrite it.
You use the power rule to rewrite?
Yes, use the power rule. And how would you write that x as a power? X to the minus 1. That's it. 5 minus 4 times x to the minus 1. That is the same as that. This I like to differentiate. I don't like trying to differentiate that. What's your f prime of x now? Second?
Negative 4x negative 2. Next one is negative 2.
Okay. I agree with most of what you said except the minus 1 times minus 4 is plus 4 x to the minus 2. Perfect. Okay? Now, that's your f prime. And what the problem said, such that f prime of C, so we're looking for values where this is equal to 1. This is equal to this thing, 1. So we need to solve that equation. Now, to solve this equation, I don't like the exponential form. So why would we write that otherwise?
4 divided by x squared
Equal 1. And where do you go from there?
Multiply that 1 by x squared.
Yep, multiply both sides by x squared. Okay, x squareds go out here. This gives you 4 is equal to x squared. And then what can you do with that?
You square root it.
Say again?
X equals 2.
All right, I was afraid you were going to say that. But it's okay in this case. Why is it okay in this case?
Because I square root it.
What's that?
Because you do the square root of it.
And when you do the square root, you should get
X equals plus or minus.
plus or minus 2. But in this case, you're okay to say 2. Why? Because the interval doesn't include minus 2. So in this case, you lucked out by just saying x equals 2, which is fine. Should be plus or minus 2, but you have to exclude the minus 2 because that's not in there. So x equals 2 is the place and the one and the only place where that derivative is 1. Okay? So basically, you've done what is asked. Find all the values of C, x equal 2, that's it, and the open interval 1 to 4, see, minus 2 wasn't in that, such that f prime of C is equal to the secant line between those 2 points, line between those 2 points, slope of that line, and that is at x equal 2. All right, now they may do more with it, but really that's all you need to do. Okay? It's a good idea to note the other stuff, but okay, first thing they did was find the slope between those 2 points. That was 1. Note that the function satisfies the conditions of the mean value theorem. Number 1, that this function is continuous on that interval. It's not continuous everywhere, not continuous at x equals 0. But on 1 to 4, it is continuous. Okay? Number 2, that it's differentiable on that interval. It's not differentiable at x equals 0. You can't do it. It's not even defined there, so you can't differentiate it there. But that's okay. On that interval, it is. And then you're okay to go. That is, f is continuous on the interval 1 to 4, and it's differentiable on that same interval 1 to 4. Continuous using the endpoint, the closed interval, differentiable on the open interval. Okay, so there exists at least one number C in that. You know that it does, so the f prime of C is equal to 1. So what you do, take the derivative. You get 4 over x squared, set it equal to 1, implies that x equals plus or minus 2. But guess what? The interval is 1 to 4, so you conclude x equal, that the C is equal to 2. Okay? Now, why they colored them in, I'm not sure. But here's your secant line from 1, 1 to 4, 4. Slope of plus 1. Okay? Here is your graph of the function. Notice it isn't even defined at x equals 0. It's going to negative infinity down here. So don't include anything over there that would throw the whole thing off. Okay? But, the one thing we did do. Once we found out that x equal 2, we needed to go back and plug in and see what the y value was. So let's go back and do that now. So when x is equal to 2, let's go back and find the function. Here it is. What is f of 2? What's that? Pretty easy to do. 3, is that what you said? 5 minus 2 is 3. Perfect. Okay. That's the one thing we didn't do. We didn't find the point. We just found the x value. Okay? Which is really all they asked, but they showed that it was at the point 2,3. And at the point 2,3, sure enough, you have a tangent line that is equal to the slope of the secant. Slope of the tangent line equal to that. And that's what mean value theorem tells us. Guess what? There's nothing average about it, you know. It's just that there is a point in between 1 and 4 where you have the same slope as you do between the points 1, 1, and 4, 4. That's a mean value theorem. Okay, a useful alternative form for the mean value theorem is that f is continuous on AB, just like before, differentiable on open interval AB, just like before. Then there exists a number C in A to B, so far so good, just like before, such that f of B is equal to f of A plus B minus A times f prime of C. You know, that's saying the same thing, because if you subtract this from both sides, you have f of B minus f of A, divide both sides by B minus A, that gives you f prime of C. It's saying the same thing, okay? Keep in mind that polynomial functions rational functions, trigonometric functions, are differentiable at all points in their domains. Okay? That is the big caveat here, in their domains. Polynomial functions, domains everywhere. Negative infinity, positive infinity. All real numbers. No problem there. Rational functions, whatever is in that denominator cannot be 0. Those are the things you exclude, so therefore it would not be in the domain. Trigonometric functions, sines and cosines, differentiable everywhere. But all your other four, secant, tangent, cosecant, cosine, tangent, they have values that they're not defined. So as long as you stay don't cross those, then in the domain this works. Okay. Just have to keep up with your domains. Oh, my goodness. That was it.
It was an example.
What's that?
It was an example.
I still couldn't get.
It was an example for.
Yeah, I know. That's what I was saying. The slideshow ended, but the examples haven't. Let me go back and do example 4. But looking at it, I'm not sure I do want to. Let's see. Finding an instantaneous rate of change. 2 stationary patrol cars are equipped with radar are 5 miles apart on a highway, shown in the figure. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles an hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour sometime during that 4-minute interval. Okay? Interesting problem. Okay? So let's sort of draw a little graph here. I'm not sure it's necessary. I'm surprised they don't. Okay. Let me just mention this. They're wanting to use this to prove this with calculus, right? It's a little silly, isn't it? Let's take a look at this. 2 stationary patrol cars, 5 miles apart on a highway. As the truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when it passes the second patrol car, its speed is clocked at 50 miles per hour. My question is, so what? Because what we have here is a truck, this is so ridiculous, a truck that moved 5 miles in 4 minutes. Right? That's what they just said. 5 miles in 4 minutes. If it did 5 miles in 5 minutes, what would be its speed? A mile per minute, which is how many miles per hour? 60. If it did it in 4 minutes, it's exceeding 60. Somewhere, right? This is a ridiculous problem. There's no reason to use the mean value theorem in it. You can prove it right there. It had to be going. Its average speed was more than 55 miles an hour, so therefore it's, yeah, there's at least one point is moving more than 55 miles an hour. So when I read this, I thought, wait, you don't need to go through any of the gyrations that they do here. But what they do is say, let t equals 0 be the time in hours when it passes the first patrol car. The time when it passes the second patrol car is a 15th of an hour later. Well, they already told you that 4 minutes later. Okay, yeah, got it. By letting s of t represent the distance in miles traveled by the truck. You have S of 0 equals 0. Yeah, that was what the distance was. And S of 1/15 of an hour as 5. So the average velocity of the truck over that 5-mile stretch would be 75 miles an hour. Okay? So guess what? It's basically almost saying the same thing I am. So therefore, without drawing a graph or anything else, if the average speed was 75 miles an hour, there's at least one place on that, in that time interval when it was traveling 75 miles an hour. Okay? So, okay. That was kind of a crazy problem. You don't have to do much of that. Homework exercises here. Do either 3 or 5. They're both at Calc Chat. Neither one of them are at Calc View. Then do either 7 or 9 or both. They're both at Calc Chat. 9 is at Calc View. Do any of the odds 11 through 23. They're all at Calc Chat. The 13 is at Calc View. Do either 25 or 27. Both are at Calc Chat. Neither are at Calc View. Now, I noticed something here. Number 25. F of x is equal to absolute value of x minus 1 on an interval -1 to 1. It says determine whether Rolle's theorem can be applied. What do you think? Okay, absolute value function. Looks like this, right? Rolle's theorem apply? No, why not?
Because it comes to
The first derivative is not defined at 0. You're absolutely right. So don't even try using Rolle's theorem. Remember the conditions for Rolle's theorem? Function must be continuous. Yep, that was continuous. No problem there. First derivative must be differentiable on that interval. Not, because it's not defined at 0. Okay. Just to point that out to you. Okay, do 29 is a Calc Chat. Do 31 is both a Calc Chat and Calc View. Do either 33 or 35. They're both a Calc Chat, but neither at Calc View. Then do 37 is a Calc Chat, not a Calc View. Do any of the odds 39 to 47. They're all at Calc Chat. 47's at Calc View. Do either 49 or 51. They're both at Calc Chat. Neither are at Calc View. Do 53. Now, it's interesting. 29 was a vertical motion problem. 53 is too. Do at least one of them, but you don't necessarily have to do both. There are some exploring concepts, 55 and 57, so you can look at those if you want to. 59 is a speed problem, so you can look at that if you'd like. 61 is a velocity problem, which sounds a lot like the other, except I think one's a plane and the other are bicyclists, so they're different values for sure. There's a think about it at 63. You can think about that if you want to. Then try to do either 65 or 67. They should both be at Calc Chat. And 69 or 71. 71. They should both be at Calc Chat. Neither at Calc View. There's true false 73 and 75. Think through those. And then there's some proofs. 77 and 79, 81, 83 are all proofs. You can try those if you want to. I'm not requiring you to, but you may find them interesting. And then 85 is using the mean value theorem, which is probably a pretty good thing to look at too. All right, any questions? That was it for 3-2. Pretty quick, huh? Okay, let's move to 3-3. Okay, another reason to mention, get working on your tests, folks, because we've already had test 1, test 2. Some people haven't turned to test 1 yet, and we're moving along reasonably well in chapter 3. So not going to be that long before we have test 3. Please get your papers in and get your test in too. Okay. I'm waiting for something, but it's not doing anything. I shouldn't have been waiting. Okay, continuing with application of differentiation. We've looked at finding your extreme values, roles in the mean value theorem. Now we're going to look at, excuse me, I got hiccups, increasing and decreasing functions and the first derivative test. What in the world is that? Okay, so what we're going to do here is determine intervals on which a function is increasing or decreasing. Increasing or decreasing. Now, let's think for a minute. What must occur if there's some interval here where it's increasing, some interval over there where it's decreasing? What must have occurred in between? Either the slope was 0 somewhere in between, because on this side, increasing function slope is positive. The other side, decreasing function slope is negative. If this had a continuous slope, meaning the first derivative was continuous, there had to be some place in there where the derivative went to 0. So we're back to our extreme value problem. Local minimum or maximum. So I think we already got most of the things we need for that now. We'll apply the first derivative test. We've got to first figure out what that is to find the relative extrema of a function. Okay? Local minimum, local maximum. That's what relative extrema are. So, increasing and decreasing functions. You will learn how derivatives can be used to classify relative extrema as either relative minima or relative maximum. First, it's important to define what an increasing and a decreasing function is. So here's the definitions. A function f is increasing on an interval when, for any two numbers, x1 and x2, that are on that interval, x1 being less than x2, that f of x1 has to be less than f of x2. That means it's an increasing function. For any two numbers, x1 and x2, that meet that bill, if f of x1 is always less than f of x2, that's an increasing function. Of course, it's a decreasing function if on that same interval, two values, x1 and x2, where x1 is less than x2, f of x1 has to be greater than, unless I'm reading this wrong, they said the same thing, which is obviously not true. That has to be a greater than sign. Yes, it was wrong in the book, and it's wrong on the slide. Those have to be greater than signs. Does your book have it? For that second one?
Yes, it's the same thing.
It does have greater than? Okay, someone came in with a red mark and put a greater than sign. I don't think, yes, it was me. I'm sorry, it was me. I remember I got a new book in, but I gave the new book to Dr. Bryant. I thought this was the first time I did that. Okay. So, wrong answer, folks. And let me put it in red too. Well, I'm already in red. This is not a less than, that's a greater than there. Okay? But you say your book already has a greater than there.
No, see,
Oh,
mine
it
has
did.
a less than yours.
Huh?
Yours, mine's similar to yours.
Okay.
It's less than.
Change that to greater than. For this to be a decreasing function, f of x1 must be greater than f of x2. I changed it in my book. I'm changing it on the presentation. Change it in your books as well. This can't be, both of them can't be true, okay? If they're the same thing, but one's decreasing, one decreasing. Well, we'd never be able to tell. So that should be greater than sign. I am really surprised. This is the 11th edition, and the fact that the error came through on the 11th edition is amazing, because this is a pretty good author. I'm really shocked at that. Okay. A function is increasing when, as x moves from left to right, we usually go that direction, left to right, or what the values are, left to right, the graph moves it up. Okay? So here, when you're moving from left to right, your function is moving up. That's an increasing function. It's decreasing when it's going down. So this one, anywhere from, it looks like negative infinity, though I can't tell this, it looks like it might be going asymptotically this way. It's sort of hard to tell, but wherever it's coming from, up until this point here, it's decreasing. Okay, it's going down. There can be a function that's called a constant function. That's why on the previous thing, they said greater than here, less than there. They didn't put equal to, because equal to would then be a constant function. Okay. So this is decreasing from negative infinity to the point A, x equal A. It's constant on the interval from A to B, and it's increasing from B to positive infinity. Okay. Now here's something I want to point out to you. It's not a big deal, but it's how the book always prints these things. Up until now, it's been very careful of whether they're open intervals or closed intervals. Okay? Notice when we're talking here, every one of them is listed as open. There's no reason you couldn't include point A here, okay, and have that being closed there, but they don't do it. Also, you could have included A and B here and had these closed here. They don't do it. Same thing here. You could have included the point B and it would still be correct. However, they don't do it. When they're talking about intervals, they usually express them as open intervals. Not a big deal unless, of course, you were working on WebAssign or something like that, and it's going to tell you it's wrong if you don't have that parentheses in there. Okay? Now, here's a theorem coming up. It shows a positive derivative implies the function is increasing, negative derivative implies it's decreasing, zero derivative over an entire interval implies it's constant in that interval. Hey, this is the application of differentiation. All that other stuff you had back in pre-calculus algebra or maybe before, but now we can use your derivative. Test for increasing and decreasing function. F is a function that is continuous on the closed interval A to B, differentiable on the open interval A to B. If F prime is greater than 0 for all the x's in that interval AB, it's increasing everywhere. And there they put the bracket here. You can only say the derivative is on an open interval, but they say it's increasing from A to B. They close it. They didn't earlier, now they are. If F prime is less than 0, that means it's a decreasing function. If it's on all the x's in here, it's decreasing everywhere from A to B. And if F prime of x is equal to 0 for all x's on some interval A to B, then it's a constant function on that interval A to B. If it's 0 for all of them. Okay? So, there's your application of differentiation. Determine whether the function is increasing, decreasing. Take the derivative, evaluate it. If it's positive, it's increasing. Negative, decreasing. 0, constant. So, find the open intervals, notice they say open intervals, on which f of x, which is x cubed minus 3 halves x squared, is increasing or decreasing. So what you reckon you're going to do first? Take a derivative sounds like a capital idea. So let me get my pen back, a dark color, and f prime of x is equal to what?
2x.
Second?
2x squared.
2 or?
2x squared.
3x squared. Okay.
I was thinking about the x squared.
Yeah, okay. 3x squared. Minus
minus
6 over 2x.
second
6 over 2x.
2x or 3x, okay? Because the 2's cancel out and that leaves you 3x. Okay, so there's your first derivative. Now it's asking for the open intervals on which that function is increasing and decreasing. So what does that mean as far as your derivatives go? You took the derivative. Why were you taking a derivative? If derivative is positive, what does that mean?
It's increasing.
Increasing. If it's negative, decreasing. So what do you think is going to be the thing that's going to be in between?
0.
0. So let's first find the zeros, where they're neither increasing or decreasing, and then we'll look at the intervals outside and in between those. So where is this equal to 0? What would we do first?
Pull out 3x.
Pull out what?
Pull out 3x.
3x, excellent. Okay. What does that leave you with?
X minus 1.
X minus 1. Okay. What does that tell you?
Your zeros are x equals 0 and x equals 1.
Okay. Those are the two places where your first derivative is 0. X equals 0 and x equals 1. So what I want to do is figure out that there the first derivative was 0, right? So I want to figure out, and by the way, notice the first derivative is defined everywhere. No places where it's not defined. So these are two critical values, critical points. Okay. See, I like to call them critical numbers. That's what they're called. Okay. So those are going to be the ones I consider. So if I go anything to the left of 0, it should not change sign. Anything in between should not change sign. And anything to the right of 1 should not change sign. So all we have to do is pick a value less than 0. What would be a good value less than 0? Negative 1. So let's take your first derivative and plug in f prime of negative 1. And what do you get? 3 times negative 1 squared minus 3 times negative 1. Okay? And what would that be? What's negative 1 squared?
It's negative 1 squared is 1.
Okay. And 3 times 1 is?
3.
Minus?
3.
No.
Positive 3.
Plus 3. 6. What does that tell you about all the values from negative infinity to 0? Increasing. So find the open intervals on which it's increasing from negative infinity to 0. Okay? Let's consider something between 0 and 1. What would be a good value? Some value between 0 and what? 0.5. Okay? So let's do f prime of 0.5. Okay? That would be 3 times 0.5 squared minus 3 times 0.5. Okay? That's 3 times, what's 0.5 squared? 0.25 minus 3 times, well, let's multiply that. That would be 1.5, right? Sorry, that was ugly. 3 times 0.5 would be 1.5, right? Agreed or not? Okay. What's 3 times 0.25? 0.75 minus 1.50, if you want to put it that way, is negative. What does that tell you about every point between 0 and 1? Decreasing between 0 and 1. Well, we still need to consider what's happening to the right of 1, so what might we consider? I wouldn't do 1. You know what it is there at 0?
Yeah.
2. Okay, f prime of 2. Let's see what happens there. That would be 3 times 2 squared minus 3 times 2. Right? What's 2 squared?
4.
3 times 4 is
12.
12 minus
6.
is?
6.
That's positive. That's the big thing. It's positive. So that means you're increasing again from 1 to infinity. Okay? These are the increasing, and this 1 is the decreasing. All right. Make sense? Less. All right. Let's see how they did it. Well, goodness, I'm getting so hungry today. I don't know why.
Well before my usual lunchtime. But
Starving. Okay. Notice that f is differentiable on the entire real number line because it's a polynomial function. Derivative of f is x cubed. No, f is x cubed minus 3 x squared. They wrote it again. And then they took the derivative. It's 3x squared minus 3x, exactly like y'all got. And to determine the critical numbers of f, set that equal to 0, which produces 3 times x minus 1. Well, 3 is never 0, so throw that out. X could be equal to 0, and x could be equal to 1. So those are your two critical numbers. I like to call them critical values or whatever. Okay? Now, what that means is, outside and in between those critical numbers, you're no longer have a 0 derivative. So that means your function is either going to be increasing or decreasing or constant in between. So because there's no points for which L prime does not exist, so it's not going to be that there's no values, you can conclude that x equals 0, x equals 1 are the only critical numbers. Okay, we did that. And all you have to do is pick a value somewhere outside of those three. Get one to the left of 0, one between 0 and 1 to the right of 1, and see what's happening. They came up with the same conclusion we did, that the f prime at -1 is 6, which is greater than 0, increasing everywhere from minus infinity to 0. From 0 to 1, notice we put them in open intervals. They chose 1/2, just like you did. They found out it was -3/4, just like you did, which means it's decreasing in between those 2 points. And then to the right of 1, they chose the value 2, looked at it, value of 6, which is greater than 0, so it's increasing as well. Okay? Same conclusions we got. Sorry. Here's the graph of it. It certainly is increasing pretty big time from -infinity to 0. Okay? Between 0 and 1. And by the way, we didn't go back and plug in. We could have. When you put 0 here, 0 there, you get 0. So the y value is 0 there. When you put a 1 here, that would be 1 minus 3/2, which is -1/2. And then you put, so 1 is -1/2. So that's the point here. Now, just that by itself, if we had evaluated those two points, you know that those are your two critical numbers. You could tell by that, if it started here and went down to here, that had to be decreasing. You didn't have to do a test point. You could have just seen that. Okay? Here you need a test point to check it out, and sure enough, they came up too. So even this one, you didn't need to do a checkpoint if you had done these 2 points, found out what the values were there. It had to be decreasing in between. Okay? No way around it because it's a continuous smooth continuous function. Okay. Now, example 1 gives you one instance of how to find intervals on which a function is increasing or decreasing. Guidelines below summarize the steps followed in that example. Okay? Guidelines for finding intervals on which the function is increasing or decreasing. Now, start with, make sure f is a continuous function on that interval a to b. If it's not, don't even try these other things. It has to be continuous. Okay? To find an open interval on which it's increasing or decreasing, use these steps. Now notice here, it didn't say anything about this first derivative. It only said the function itself. Okay? So what we do, locate the critical numbers of f. Well, what are they? You tell me what the critical numbers are. Where? Okay. How do you determine the critical numbers? I call critical values, whatever.
When you say it equals 0 and when it's...
Your first derivative equals 0 or... What's the other condition? You might have. We did in the last example. Where's what?
It's not differentiable.
Yes, exactly. Where the first derivative does not exist. Exactly. Where the first derivative is 0 or where the first derivative does not exist. Those are your critical numbers. Okay? Use those numbers to determine the test intervals. Okay. Now notice here, the function has to be differentiable or you can't tell that. Okay? So they left that out here, but it has to be differentiable on the open interval. It has to be continuously also differentiable. It may not exist at all the things, but it has to be differentiable. Okay. The function has to be differentiable. Determine the sign of f prime at your test numbers. So if you have the test intervals, 0, 3, 7, and 14, maybe a -1 in there. Do something left, between, right. Okay? Get all the intervals, identify them, pick a number for a test value, not at the point, outside the point or between the points. Okay? And then use the theorem to determine whether it's increasing or decreasing on the interval. Those guidelines are also valid when the interval a to b is replaced by interval negative infinity to b, a to infinity, or negative infinity to infinity. Okay? That would be all the numbers. Okay. I don't know really why they include that. That's everything. Okay. Now, here's another term for you. A function is strictly monotonic. What does that mean? What does the prefix mono mean? One. Okay. That's key. Think one direction. Okay? A function is strictly monotonic on an interval when it is either increasing on the entire interval or decreasing on the entire interval. For instance, this function here, f of x equals x cubed. Okay? It's increasing here. Now, it looks like it might be constant somewhere in there, possibly. It looks awfully flat there. It's increasing there. So definitely the first derivative is 0 there, so that would be a critical value, but that's not an extreme value because it never backs up on itself. Okay? And if you were to pick closer and closer to 0, you'll find out it's always either slightly below or slightly above the x-axis, except right at 0. So that is increasing everywhere on the entire number line, negative infinity to infinity. That's where you'll see that. Okay? No place is decreasing and no place is constant. Even there where it looks awfully flat, it's still slightly, very slightly increasing. Okay? Monotonic. Now, it doesn't have to be increasing. You could have monotonic decreasing as well. As long as it doesn't ever go to 0, well, there's no interval on which it goes to 0 or changes its sign. Okay? So the function shown in this figure here is not strictly monotonic because it is, okay, here's the function. F of x is equal to this thing right here for x, this thing right here, minus x squared for x less than 0, 0 between 0 and 1, and x minus 1 squared for x greater than 1. Okay? Well, this is increasing everywhere here. Why? Because the first root would be a minus 2x, right? But all your x values are negative. So you put a negative value, multiply it by negative 2, it's always going to be positive. So this is increasing everywhere up to 0. But it's 0 between 0 and 1. And then this function, x minus 1 squared, is always positive, and the larger the x is, the bigger and bigger that number is, so that's strictly increasing as well. Okay? But this is not monotonic because it's not increasing everywhere. Increasing here, but not increasing here. You put any value in here and it doesn't change value. Any 0.5 is still 0, 0.7 is still 0, 0.1 is still 0. So there's no place in there that it's ever increasing. It's constant. Okay. All right. All right. This section sure starts with a lot of blah, 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 doesn't it? The first derivative test. More blah, blah, blah. After you have determined the intervals on which a function is increasing or decreasing, it's not difficult to locate the relative extrema of the function. Okay? For instance, in figure 318, the one we did earlier, example 1, the function has a relative maximum at a point 0, 0. Okay? A relative minimum at 1, negative 1 half. Okay? And why that is a relative maximum? Because it was increasing up to then, decreasing after that, that had to be a maximum. Why this was a minimum? Decreasing before, increasing afterward, had to be a relative minimum.
Is that what you meant by backing up on itself? Or
What's that?
you was talking previously, you were saying something backing up on itself. Is that what you're talking about when it's...
Yeah, when the function backs up on itself, it was increasing, then it goes decreasing, then it changes direction. Okay. There are other times I might use that terminology to indicate it's not a function if it backs up on itself that way. But if it does this way. Okay. All right. So just because it has a critical number there doesn't guarantee it's a relative maximum or minimum. The first derivative test will tell you it's positive over here, negative here. It has to be relative maximum. Negative here, positive there, it tells you that has to be a relative minimum. Okay. Similarly, I'm sorry, I did it. F has a relative minimum at the point 1, negative 1 half because it's decreasing immediately to the left of x equal 1, increasing immediately to the right of x equal 1, therefore it has to be a minimum there. Okay, and this theorem that they've got coming up here, oh, here it is. I was looking for it in the book, and there it's got all these figures on it. The first derivative test. Let C be a critical number. How do we find those critical numbers?
By taking the derivative.
Take the derivative first, and what?
0. And by making it 0.
That's one way, or where that derivative does not exist. Okay. Two places where it can be a critical value, critical number, where the first derivative is 0 or where the first derivative does not exist. Okay? Okay, let C be a critical number. That's one of those. Where the function f that is continuous. The function f has to be continuous on the open interval containing C, all those critical numbers. and if it's differentiable on that interval, except possibly at C, differentiable everywhere else, then f of C is classified as follows. Okay? Now remember, just because it's a critical number doesn't guarantee it's a maximum or minimum. Okay? So if f prime it changes from negative to positive at C, from negative on this side to positive on that side, that has to be a relative minimum. Has to be. If f prime changes from positive to negative at C, it has to be a relative maximum. If f prime of C is positive on both sides or negative on both sides, then it's neither a relative minimum or maximum. So here, f prime is negative, 0, positive. Got to be relative minimum. Here, f prime is positive, 0, negative, has to be a relative maximum. Here it's positive, 0, positive, neither. Okay? It's neither a maximum or minimum. Or if it's negative, 0, negative, neither. Okay? Not an extreme value. These are not. Don't give a name for those later. I keep wanting to say it now, but we'll come up with it a little bit later. Okay. Here's example 2. Finally, after pages and pages, we get to example 2. Oh my goodness, is it time? It is. Shucks. Thank you. Thanks for watching. Since my watch broke, I don't look at it often enough. So we'll pick up there, top of the page. Is where I ended last time. I don't know if we got far enough along for any. Well, yeah, we should have. Do number 3. You should be able to do that. I think you can do any of the odds 5 through 9. They're all at Calc Chat. 5 is at Calc View. And we'll hold off there. We'll pick up the rest up. Well, no. We did first derivative test. To do any of the odds 11 through 17, they're all at Calc Chat. 13's at Calc View. And then do any of the odds 19 to 39, they're all at Calc Chat. 21's at Calc View. Do any of the odds 41 to 47, they're all at Calc Chat. 41's at Calc View. And we'll stop there. Okay. Good deal. All right. Have a good weekend. Working on calculus will make it good, right? All right. And papers. Okay, good deal. What's that?
So I gotta get the paper turned in.
Okay.
I have to get that paper turned in.
Oh, okay, good.
I get that test number 2?
No, it's too late now. You got a 0 and it's over with, okay? All right. Test 2.
How did that run?
You too.
Yeah, I'm sorry I've been missing some of these classes. I'm
working like crazy.
yeah, I've been working a lot everything because I usually work on Mondays, so I've been having to miss some of the Mondays.
Yeah,
Some
I
have also
noticed.
had to come sometimes, but I know it's okay because I watch most of them online. So
Why do I not have enough copies of this?
It's students.
Pretty sure I made enough.
I mean, you can give it to me Monday.
No, I'll go run and make a copy now. I think somebody must have gotten 2.
So we did hand out 2 copies to one person because he was going to give it to somebody else.
Yeah, maybe then that person got it. Okay, that's probably exactly what happened. Glad you remembered that better than me. Okay, let's run down. You got one, right? Okay. Let me, if you don't mind, let me